Well, we're starting night chapter 6, motion along a line. Now, if you're having deja vu, chapter 2 was titled Kinematics in One Dimension. That sounds mighty suspiciously similar to this chapter. Are we just doing things over again? Well, no. Motion along a line now is not just the description of motion, but the explanation of motion in terms of forces. So yes, a lot of the problems here are going to boil down to problems that you've seen in chapter 2, but you're now approaching them from free body diagrams, including all the different forces in the force catalog that show up in those free body diagrams. Now, 6.1 is a special case. Okay, he starts off this whole business about motion along a line in a special case. Okay, so this is the equilibrium situation is no motion at all. So here I've got some particle and I've got several forces on it. Okay, I just drew several forces kind of at random. Now that's not going to work. That's not going to be an equilibrium situation because it looks like I've definitely got more pulling this direction than I have pulling that direction. So let's give me one more force in that direction. And maybe I've managed to draw things so that F net, the sum of force 1, force 2, force 3, force 4, and force 5 adds up to 0. If you have that situation, then the right-hand side of F equals MA is 0, 2. So we have F net equals 0, but we also have F net equals MA, and therefore acceleration is equal to 0. So this very interesting special case is the case where acceleration is 0. That means the velocity is unchanging. The velocity is unchanging, we can always choose some reference frame where the velocity is 0 and just go hang out with this thing that is at rest. I'll tell you, I can also stand that on its head. I can say if I have something that is at rest or I have something that is in constant velocity as its motion, in either of those two situations, I immediately deduce that A equals 0. And from that, I can go the other way and say, hey, F net must be 0. So this business about equilibrium, it can go two directions. You can either observe that something has no acceleration and then deduce what that means about the forces, or you can be given a set of forces which add up to 0, in which case you deduce, if that's what you discover, then you deduce that A equals 0. Now you might think we're all done with this, but let's go look at example 6.2. Example 6.2 is a car on a hillside and there's a tow rope on the car. So here's the car sitting there on the hillside and there's a tow rope hitched to the front of the car. Let's draw the free body diagram for this car. We know that there's the force of gravity going downwards. We know that if I draw a perpendicular to this hillside, that there's a normal force on the car that is perpendicular to the hillside. We also, let's just assume here that these wheels roll really easily, okay? So we don't have to worry about that there's some friction pulling that way or friction pulling that way. Let's assume that this car has been set so that its parking brake isn't on and it's not running. So there's no force in this direction of the pavement on the wheels. So then there's just one more thing. This rope over here has a tension, and let's draw that going that way, parallel to the hillside. So there's your free body diagram. Let's assume it's not accelerating up the hillside, it's not accelerating down the hillside. It might be moving steadily up the hillside or moving steadily down the hillside, or it might be stopped, but in any case, it is not accelerating. Then we have A equals 0, or MA equals 0, or F net, which is equal to MA, must be 0. Now, what does that tell us? You might think it tells us nothing, but it actually tells us quite a lot. Let's draw a useful coordinate system in here. I've drawn one axis that's parallel to the hillside. I'll call that the x-axis. And I've drawn one axis that's perpendicular to the hillside. I'll call that to the y-axis. Now I can play a little game here. You've seen me do this quite a few times now. I resolve this vector, which is not pointing parallel to the x-axis or pointing parallel to the y-axis. I resolve it into two vectors that do. There's the amount of this vector that is parallel to that axis, and there's the amount of this vector that's perpendicular to that axis. Now, looks like I've drawn things decently well. It looks to me like this vector here that I've called n is about the same length as this vector here, which is the component of f sub g that is parallel to the y-axis. So it's quite believable that this vector that I've circled and this vector just cancel each other out. What's left? Well, this vector here, this one that's I've labeled t, that's got some magnitude, which I can call t, and then it's got it's multiplied by something in the I hat direction. This one here, well, there's an angle here, okay? So there's an angle there that we're going to call theta. And it looks to me like this one here is however big f sub g is. Now, f sub g is a vector. The thing that I say how big f sub g is that same thing with no vector sign, okay? So I just erased the vector sign off of that quite deliberately. That's the magnitude of f sub g. The magnitude of f sub g times, now I can see that it's pointing in the minus x direction, so it must be a minus I hat. And I can see that the amount here, that's an opposite over hypotenuse kind of situation that tells me the relationship between the long side, the hypotenuse side, and this side. So since that's opposite over hypotenuse, that's sine theta. So there is this vector right here. It's equal to minus fg sine theta I hat. And here's this vector right here. It's equal to t I hat. Now we know that the sum of all the forces has to add up to 0. That means that the sum of all the x components has to add up to 0. So let's just do the x components here. That's this part here is plus t I hat minus fg sine theta I hat is equal to 0. Okay, so that I kind of wrote it out as the vector part of this. I can actually just make this a component equation, and now it's just t minus fg sine theta is equal to 0. Tension required is t is equal to fg sine theta. So there's a algebraic statement of the fact that this vector should be drawn with about the same length as that vector. So it looks like I've drawn t too long here. A more realistic diagram would have had t looking about like that. And we learned that from this equilibrium situation. To recap, what I've drawn, what I've derived, is true if and only if the acceleration of the car in this x direction is 0. If you have non-zero acceleration, you can't make this argument. Now we're going to go on to 6.2.